Good morning, Dr. Ng. Long time no see. How are things going for research project?
Hi, I'm currently doing research on miRNA disease. Things are not going as I expected. The experiments done are time-consuming and cost-ineffective. I'm finding alternative to make things work.
I see. Can you further explain about miRNA-disease? Perhaps I can help out.
Sure, it's my pleasure. I hope it won't be boring for you. First of all, miRNA are short conserved as single-stranded RNA that binds to mRNA, which in turn causes silence of the gene and represses translation of the gene. Therefore, if miRNA are found to be associated with a certain disease, miRNA will be a promising medicine to cure diseases as miRNAs are involved in various biological processes.
Oh, something crosses my mind. I think I can build a machine learning model to predict the miRNA disease association. Are you familiar with the machine learning?
I heard it before but never had a chance to try it.
Oh, I see. Let me explain a little bit about it. So basically, the machine learning is a subfield of artificial intelligence which utilizes data and algorithms to imitate human intelligence to perform the complete task. And this will greatly reduce the cost because computational analysis is involved early, and this also can reduce a lot of time.
Great, I think this could work. Would you like to join me on my current project?
Sure, it's my honor to participate. I will prepare a proposal and show it to you on our next meetup. See you then.
Nice. See you soon. Thanks for helping.
Day 2, Day 3, Day 4. A few moments later.
Good day everyone, this is Dr. Lee, a colleague of Dr. Yong. Since I have more experience in developing models, I'm joining this research project as well. Unfortunately, due to our busy schedule, we have to arrange an online meeting. Alright, without further ado, let's begin. Today, I'll be sharing about machine learning applications in the field of biomedical sciences. Before we begin, let us look at the content outline today. We will be sharing about supervised machine learning and its applications in the prediction of miRNA disease, similarity features used in the model, types of model use, critical issues in existing approaches and solutions, data and experimental setup, and also results and discussion. First of all, what is supervised machine learning? It is a label training data set used to train machines to predict the outcome accurately. We can utilize supervised machine learning in the prediction of miRNA disease. This can be done by using a dataset of known miRNA diseases association to train the model to predict the possible miRNA diseases associated pairs. The model used in this research will be based on supervised machine learning. Moving on to the second part of our sharing, we will be using 4 similarity features in the models, including disease similarity, miRNA sequence similarity, miRNA functional similarity, and also Gaussian interaction profile (GIP) kernel similarity. The mathematical equations used in each of the features are listed as shown on the screen, and they are labeled with numbers. As for disease similarity, the semantic similarity of 2 diseases is calculated based on their own positions on disease-directed acyclic graph (DAG). Next, miRNA sequence similarity works based on the similarity of 2 miRNA sequences as defined as the Euclidean distance between 2 vectors defined in the 2D representations according to the parameter sets. On the other hand, miRNA functional similarity is estimated according to the similarities of the diseases it is associated with. The last similarity feature, GIP kernel similarity, utilizes the miRNA disease association matrix and a few parameters listed on the screen to define the similarity between 2 miRNA sequences. I know this might sound boring, but please bear with me. Next, the similarity features are then implemented in the models. The models used in this research design are EPMDA, NIMCGCN, and also DBMDA. Let's talk about EPMDA first. EPMDA stands for Age Perturbation-Based Method for mRNA Disease Association Prediction. From the name itself, we can know that the extraction method is based on age perturbation in an mRNA disease heterogeneous network. Feature extraction model can be done using this model: miRNA disease bipartite network, miRNA similarity network, and disease similarity network are combined to form a heterogeneous network G as an input into EPMDA. The miRNA disease bipartite network consists of 2 nodes which include mRNA and disease. If there is a non-association between mRNA and disease, there will be no connection between 2 nodes of the same type and a link between mRNA and disease node. As for the mRNA similarity network, it is a weighted network with each node representing mRNA, and the weight of the each corresponds to GIP kernel similarity between 2 mRNA nodes as defined in equation 6. On the other hand, a disease similarity network is a weighted network Each node is a disease, and the weight of the age corresponds to disease GIP kernel similarity, as shown in equation 7 in the previous slide. Let us look into the steps involved in the APMDA model. Feature extraction is performed in APMDA. Disturbance level, Fi, as a result of the deletion of a particular age in G, reflects the disturbance level due to that particular deletion. The interpretation of the model is that the higher the disturbance level, the more significant that particular age is. A 5-layer multi-layer perceptron regression model is trained using results from extracted features. This shows the prediction of association between miRNA disease pair. We will now move on to the next model, which is the NIM-CGCN. It stands for Neural Inductive Matrix Completion with Graph Convolutional Network. This model works based on the heterogeneous mRNA disease association. It consists of two nodes, which are mRNA and diseases. Disease node form disease semantic similarity, at which age weights are defined by disease semantic similarity score. Equation 4 calculates the disease semantic score. On the other hand, miRNA nodes from miRNA functional similarity network, at which age weights are associated with the miRNA functional similarity score, as calculated from equation 5. If there is a link between miRNA and disease node, this indicates a non-association. Two graph convolution networks, GCN, are used to study node representations for both mRNA functional similarity network and disease similarity network separately. Neural projections are implemented on the learned representation for the extraction of latent features corresponding to miRNA and disease correspondingly. Thirdly, DBMDA stands for Distance-Based Sequence Similarity for miRNA disease association prediction. This combines information on miRNA sequence, miRNA functional similarity, miRNA disease associations, and disease semantic similarity. When the miRNA disease pair is inserted in this model, it will first connect together by disease similarity and miRNA function similarity, as shown on the screen. Autoencoder is used to extract joint low-dimensional representation using autoencoder 1. You might now be questioning where the miRNA sequence similarity fits into this model. miRNA sequence similarity features are fed into autoencoder 2 to extract latent representations corresponding to miRNA sequence. The extracted representations are then linked together and fed into the rotation forest classifier for the prediction of the association of miRNA disease associations. That is all for my part. Now I'll be passing to my colleague to continue the sharing today. Thank you.
It's Dr. Yong here. So thank you to my colleagues, and now I will proceed to the proposal, which we're talking about the critical issues and assisting approaches and solutions. There are three major critical issues that will be assessed in these approaches, which are the data leakage problem, the evaluation setup, and the model building problem. Alright, so now I'll be talking about the first issue, which is the data leakage in machine learning. But before that, you must understand what is training set and test set. So for the training set is used to learn the model parameters, while for the test set is used for evaluating the model's predictive capability on unseen data. So the data leakage occurs when the information from the testing set is used during the training phase, leading to an overestimation of the model predictive power and an unfair comparisons between models. So miRNA functional similarities and GIP kernel similarities commonly used in miRNA disease association prediction suffer from data leakage. They provide an example using the MISIM database as the source of miRNA functional similarity. The functional similarities in miSIM version 1 MOIO and 2.0 are computed from the HMDD 2.0 and HMDD 3.0 respectively. However, these pre-computed similarities for training and evaluating models violates the rules of only using the training set information. So the solution for this problem is to propose a fix by offering an evaluation framework with the code that calculation miRNA functional, disease semantic, and GIP similarities solely from the associations in the training set. And next issue is the evaluation setup. Here is dividing into three parts. So the first one is the random seeds. The use of random seeds during 5-fold cross-validation can lead to different data splits and results, even for the same model. To address this, reporting the average performance scores for multiple random seeds. Secondly is the choice and quality of negative training and testing sets significantly impact the model performance. So the non-miRNA disease associations indicates the positive samples, whereas the unknown miRNA disease pairs indicates the potential negative samples. Using the entire set of non-connected pairs as negative training samples can create imbalanced data, leading to bias predictions. In terms of testing, a system that evaluated only on a small subset of all possible miRNA disease pairs. So it is hard to get a global rank list of miRNA associated with a particular disease. So the solution for this problem is to include all the negative pairs as considered more realistic by excluding those in the training set. The next is the evaluation matrix. So this evaluation matrix should be taken into consideration as well. There are three measurements that are often used, which are top K predictive rate, area under the receiver operating characteristic curve, AUROC, and the area under the precision recall curve, AUPRC. So the top K is the most used system as the validation method for case study. Top K scores can be misleading when database overlap substantially. So the solution for this problem is to separate the testing non-overlapping test set with the training set. And for AUROC, will be misleading for highly imbalanced data sets like the HMDD 2.0 and HMDD 3.0. Thus, the AUPRC is considered more appropriate than AUROC, using the average precision AP instead of the sklearn function for calculating the area under the precision recall curve. So the next issue is the model building problem. So the complex model that we use has pros and cons. For the pros, the more complex models can introduce non-linearity that can potentially improve the performance, but also have a higher risk of overfitting. The next is that these complex models have a larger number of parameters, requiring a larger training dataset to avoid overfitting. However, the available positive training data is limited and small in size. So to address this issue, proper evaluation studies should be conducted to assess whether the added elements in the model or features as input to the system genuinely contribute to improve the performance. Larger feature spaces can lead to increased number of parameters and subsequently overfitting. So the experiment that we carried out showed that the simple variant of the models also perform well and even outperform the original model significantly. So next we'll talk about our data and experimental setup. So for the data collection, we use two datasets. The first dataset is derived from HMDD 2.0 and the second dataset is derived from HMDD 3.0. Basically, the data collect are the number of mRNA, disease, and known associations. We also collect data regarding the number of diseases that are not found in MESH. So basically, there are 55 and 360 diseases which are not found in MESH and HMDD2 and HMDD3 respectively. For those diseases, we will fill in the similarity matrix with their corresponding Gaussian interaction profile, GIP, chromo-similarity. So for our experimental setup, right, the first one is the data split. The models are trained and tested using the 5-fold cross-validation with different random seeds. This process of each model is repeated 5 times, resulting in 25 combinations of training and testing splits. So the next is the training and testing data setup. All the unknown miRNA disease pairs are considered negative samples. So the training data can be either balanced or imbalanced, while the testing data includes the complete set of negative samples. The next one is the input similarities. We use the same set of the similarities as proposed before, like the GIP is for EPMDA, the miRNA functional disease semantic similarity is for NIMGCN. While the miRNA functional and disease semantic and also the miRNA sequence similarity is for DBMDA. These similarities are computed using only the association present in the training data to avoid data leakage that I mentioned just now. Specific hyperparameter settings are used for each model. For DBMDA, an autoencoder with an encoder and a decoder is used. While for the NIMGCN, use parameters such as number of epoch and hidden units. While for the EPMGA, utilize the code and settings for both features calculation and the MLP regression model. So now we look at our results and discussion. The first one is the impact of pre-computed similarities. As shown in the figure 3 in the left-hand side, the histogram shows the comparison of the AUROC and AP scores of the three models, which are the EPMDA, NIMGCN, and DBMDA on HMDD2 datasets. So at here, you must know that erroneous result is use pre-computed similarities, and the correct result here means the use of similarities calculated at running using only the training data. The result shows that using pre-calculated similarities leads to higher AUROC and IP scores, indicating a potential data leakage problem. So at here you must know different models are affected to varying degree. So like EPMDA, experienced the highest performance drop due to it only involving GIP chromosimilarities computed using only the association information. While for the NIM-GCN and DBMDA, which utilize disease semantic similarities calculated from disease ontology and not from the miRNA disease association, show a lower impact from the data leakage issue. But also the DBMDA in particular is more robust due to the inclusion of mRNA sequence similarity features that can be computed independently from the associations. So DBMDA is the least affected of all the models. Next, we'll talk about the balance versus imbalance data. This figure shows the comparison of AP scores between balanced and imbalanced training datasets on selected methods. It is not that the performance of DBMDA and its variance is significantly lower compared to other methods and thus not included in the comparison. So for NIM-GCN and its variant, an imbalanced training dataset slightly improved the performance on the HMDD2 dataset, but this improvement is not observed on the HMDD3 dataset. While for EPMDA, fusing an imbalanced training dataset leads to higher AP scores on both datasets. However, for EPMDA1, the imbalanced training dataset does not result in improved performance. So based on the result, we can see that the best AP score on the HMDD2 dataset is achieved by EPMDA1 with a balanced training set, while the best AP score on the HMDD3 dataset is attained by NIM-GCN3 with a balanced training set also. Therefore, this indicates that we have to use a balanced training set for our models. The next part of the discussion is about the impact of model architecture by comparing the original models with several proposal variants on the HMDD2 and HMDD3 datasets. The mean AP scores and standard deviation are presented in Figure 4, while Table 4 shows the top K evaluation results for the models and their best performing variants on the HMDD2 dataset using a balanced training data setup. So based on the result, we can conclude that the simpler variants of the models exhibit lower standard deviations in performance score across multiple data splits compared to the original models, and this indicates that its performance is more consistent, increasing confidence in their decisions. In terms of average AP scores, the best performing models on both datasets are the proposed light-weighted variants. The EPMDA1 achieved the highest AP score on HMDD2, and the NIM-GCN3 significantly outperforms other models on HMDD3. On the other hand, in terms of top K evaluation, the best performing variant on the HMDD2 dataset performs comparably or even better than the original models. Therefore, the simple variants of the models demonstrate competitive performance and, in some cases, even outperform the original models. It is important to conduct proper aberration studies when introducing additional components or information to the model architecture. So now I will make a short conclusion for our proposal. In conclusion, there are three machine learning models that we introduced in the earlier just now that are available for predicting the miRNA disease association, which are the EPMDA, NIM-GCN, and DBMDA. These models consist of input features that are extracted from the information such as the disease semantic similarity, miRNA disease association information, and miRNA functional similarity. On the other hand, there are three major issues that present in these models which lead to overestimation of the performance, affect the impartiality of comparing different models, and impede the progress of developing the models. So the first issue is the data leakage, which occurs when associations from the testing set are used to calculate the input features during the training phase. And the second issue is related to the evaluation setup, including the use of random seed, the construction of training and testing data, and the use of unreliable evaluation metrics. And the third issue discussed is the tendency to introduce more complex architectures or input features, which this can cause overfitting and increase the variance in the function of models. However, this issue can be addressed by calculating right input similarities from the training data only, and also include all the negative pairs in the complete test set, and also use the AP scores. Besides that, the aberration study should be conducted before adding the new input features to the system. Therefore, machine learning is a valuable tool for interpreting large volumes of genomics data, which plays a crucial role in functional annotation, aiding miRNA disease association prediction. I hope that you learned some new things from this proposal. Thank you. That's all from us.
Thank you for sharing, Dr. Yong. It's a new input for me, but I believe that machine learning has the capacity to enhance the outcome of my research in the field of miRNA disease associations.
Yes, of course. I hope we can collaborate in this miRNA disease association field in the future.